So thank you very much, Alicia. And thank you for coming to my lectures. And I can find many new faces, younger students probably. So although there are many senior professors, but my talk is mostly dedicated to how to inspire younger generations and looking back myself in the younger generations. Okay. So first of all, I'm very happy to be here because Uzbekistan is one of the friend country in the Silk Road. I hope Silk Road will reach beyond Beijing to Korea and Tokyo as well. And actually, my family was very old, almost 500 years family, and we communicated with China and Uzbekistan and some other countries for trading some silk. So I'm very happy to get back to our friend country. And today, I would like to discuss the origin and evolution of the universe, because we are now in Uzbekistan, and there was a famous astronomer and the granddaughter of a great leaders, and this is, as you know, the solar observatory, and it is quite precise to determine the position and movement of orbitals of planets. So I visited here several times, and I was very happy to find that this country has a very long, glorious history in astronomy. So in this sense, I'm very happy to talk about the universe. But now, today, we will discuss not only the origin and the evolution of the universe, but also the matter, asking who you are, where you are from. So matter and the universe, that is today's subject to discuss. Okay, let us start our discussion from a very profound ancient question. What is the origin of matter? In this, years, or more than 2,000 years ago, Greek philosopher Democritus asked himself, what is the world made of? And he proposed that, you see, there might be uncuttable, invisible elements, which he calls atom. Really, in the last 100 or 200 years, we humans discovered the existence of atom, and moreover, as we will discuss today, physicists found more fundamental structure, elementary particles, and nucleus inside the atom. So his prediction was correct. This is microscopic side of our universe. But when you come to just 1,000 times bigger than human size, city, continent, Earth, galaxy, cosmos. Let me say, this is not the United States, this is us. Okay, in the different extreme, gigantic scale, Albert Einstein asked, what is the origin of space-time? How was the universe begin? How did the universe begin? Sorry, this is a mistake. Okay, so we now discuss how to connect this end of the small microscopic world together with the macroscopic universe. And why universe? Because, we would like to know where we are from, our origin, the origin of matter, origin of creatures, and if our science can get some answer where we are from. Science is believed to be having a predictive power. So we should predict the future destiny, and we'd like to know where to go. In order to predict this future of ourselves and this world, this Earth, this universe, we are studying the science. Okay, first of all, I want to come back almost 35 years ago when I was still very young as you are. I was a student in the physics major, and here we show our heroine at my student days. Do you know her? She is the pop singer named Olivia Newton-John, who is singer but also grandchild of quantum physicist Max Born. Because of this, she was our heroine, and also, you know, physicists are very poor and dirty every day. You have an experiment. However, in our mind, we are always looking for beauty. Therefore, we are looking for the beauty. Okay, now, what are you made of? In order to do that, to make an answer, let us resolve this, you know, beautiful eye. You can easily get the DNA, as you see. But you have zoom in by 100%, you can get into the atom and electron clouds, see. But you have just moved in to the microscopic world, 100,000 times smaller scale, you can get the nucleus, which consists of neutron and proton. So this is a world as Democritus predicted. Now, having this beautiful face and beautiful hierarchical structure, we should study the 4 fundamental interactions. One is gravity, to keep this beautiful face as beautiful as she is, and electromagnetism, to make an atom, electron, bound by charged particle protons. Electromagnetism, gravity, and also weakly interacting leptons. Electrons exist here, and finally, to bind nucleons, protons and neutrons, into a very small size, about 10 to the minus 13 centimeter, we need a strong nuclear force. So these 4 interactions are the fundamental interaction to make this universe so beautiful. How do you know the other forces? I know. Economic power, economic force, political force, but today we don't touch about these political or economic force, just the fundamental forces. And concerning the fundamental forces, we have a so-called standard model of elementary particles and nuclei, fields. Here we show the elementary particles, which consist of all matter in the universe. Just 17 particles and the fields, quarks, neutral and charged leptons, and gauge particles, including photons, and Higgs particle, which make some mass. All these 17 elementary particles making this variety of humans and the nature. It's an amazing fact. Only graviton has not yet been discovered, but all the other elementary particles and fields have ever been discovered by a modern scientist. I'm originally from Japan, so please allow me to just refer the Japanese Nobel Prize laureates. And Koshiba was my mentor in the undergraduate courses. He discovered the neutrino from supernova 1987A, which appeared in large Magellan cloud. So I loved neutrinos. But when I was a student, she did not look for neutrinos. Proton decay. So proton decay is very profound due to the CP evaluation and others. But I wanted to do more weakly interacting charming particles. So in the PhD, I said goodbye, Professor Koshiba, and come to the theory. So I will now introduce more what I found. Yukawa is, yeah, okay. Good father. Sorry, thank you. Next time I will show. Now coming back to our question today, where were these elementary particles created? This question is related. How does the universe begin? And the recent so-called unified theory, superstring, or M theory, predicts that our Einstein fourth-dimensional space-time was created as a bubble of baby universe. If this bubble of our baby universe can grow, we could enjoy our life today. Our universe is so big. But the beginning was very, very small. This time times the velocity of light. It is smaller than the nucleus and nucleon. So our universe and the neighboring universe, which we call them the multiverse, because it is not a unique universe, multiverse were created from nothing in quantum fluctuations out of probably 11th dimensional manifold. This is a prediction of unified theory. Okay, if you like it, please write any novel. But we as a scientist, to say is easy, but to verify is not so easy. So when I was young, I tried to verify what is this kind of observational evidence. So together with my international collaborators, I tried to find it and get one of the possible observables. The idea is the following. Here, you see, this is our baby universe, just born, and it is fluctuating. Production, disappearance, appearance, disappearance. And the neighboring universe and many other baby universes exist. And if this is a microscopic size, this universe of ours and the neighboring universe, these are described by a quantum wave function. And we know waves, which are the probabilities of existence in quantum mechanics, interfere. So if these two baby universes were born, these as a wave and interfere to have a quantum entanglement. So this happened in a higher dimensional manifold. But our space is just 4-dimensional. So here, for example, we live in a 4th-dimensional space-time. But everywhere in your fingers, eyes, and everywhere, the 5th dimension or higher dimension is compactified. This should exist. At the beginning universe, they are equally existing. So our theoretical assumption and prediction is these quantum entanglement could be observables. And our universe, in one direction, everywhere, there is some quantum flow towards the neighboring universe. And we finally found that along the line of sight towards Virgo infall, beyond Virgo infall, we could find the direction of movement of matter. And this has been done by using the analysis of supernova 1A redshift magnitude relations. And this reminds you, 2011, the discovery of acceleratingly expanding universe was confirmed by analyzing the type 1 supernova redshift magnitude relation. And Brian Schmidt, Nobel Prize laureate, is one of the collaborators at almost the same age. So I asked him, please give us your data to get a Nobel Prize. We can analyze more precisely, better than your analysis. And then we could find this dark flow. I believe this is one of the observables of a quantum entanglement of a baby universes, multiverse. But there might be many more observational tests needed to verify it. This is just one possible observables. Okay, now, the similar but the different question is why could the born universe expand. And expanding universe was discovered by Edwin Hubble in almost 100 years ago. But why? The answer was given by Nambu Yoichiro, who proposed a mechanism of Higgs spontaneous symmetry breaking. Because of the symmetry of our space-time, and the particles and the fields were spontaneously broken. In the early in the early universe was just here in the simple potential, lowest minimum energy. However, because of phase transition, like a phase transition from water to ice, much lower energy level could appear in the fluctuation. And symmetry was spontaneously broken. And because of this, once symmetry was broken, it is by force keeping expansions. So now, if the universe expanded from the birth of nothing, vacuum energy is released as a latent heat. And the heat can make the elementary particles, photons, neutrinos, electrons, quarks, and their antiparticles. And once these are created, photon can make a space to high temperature, heat up. And at these high temperatures, these elementary particles interact with each other to form proton, neutron, helium-4, and others. So this is a scenario of hot Big Bang. Universe started from before a hot Big Bang fluctuation, and then after the phase transition of spontaneous symmetry breaking, elementary particles and nuclei were created in the space. This is what we believe. Okay, now let's come to the main course of our discussion today. Here we show the cosmic history, the origin of space-time we have discussed until the present day. We are now in 13.8 billion years after the creation of space-time. And where did matter started? So this is a hot Big Bang, like a fusion machine. Therefore, from elementary particles of protons and neutrons, some heavier nuclei could create it by fusion. And about this scenario, I will tell you the famous story, which everybody may know. George Gamow, who proposed that the universe started from Big Bang fireball in 1948. I was not born at this time, but after born, long years since then, my father gave me a book written by George Gamow. He was a novel to make a story for babies. It was a book, Wonderland. And in that book, he wrote many, many interesting stories. So when I was a kid, I wanted to know more about George Gamow. And sometimes I would like to discuss with George Gamow about something science, where we are born and why universe exists here, and so on and so on. Okay, anyway, in this year, long years ago, George Gamow proposed Big Bang was the beginning of our space-time universe. But quickly, his friend, Sir Fred Hoyle, who is also a very famous cosmologist, announced for the public, my friend, George Gamow, proposed our universe started from Big Bang. I don't believe it, he said. He is a big liar. And proposed steady-state universe models to keep the universe static forever. A very famous story. And since then, these two great scientists were always competing or the discussion scientifically. But it's a very good debate. Which was right? Which do you believe was correct scientifically? Of course, you know, almost 15 years ago, years after the proposal, Peng and Wilson, who were working PhD in a telephone laboratory, Bell laboratory, to find by accident the background fluctuations of radio waves coming from any different directions of the universe. And that was quickly understood by many cosmologists. Oh, it was a remnant of cosmic microwave background radiation from the Big Bang. And then Big Bang model was start being established. Here we show one of the prediction, what kind of nuclei are created. In the George Gamow standard homogeneous Big Bang model, nuclear fusion starts from protons and neutrons. Deuterium, tritium, helium-4 are easily created because it is a fusion machine. But the universe expands and the temperature cools very quickly in 100 minutes or so. So in his Big Bang model, the heaviest nucleus is lithium-7, mass 7. It is a consequence of his model. But I suspected he is a great hero of mine from my baby days, but something is missing. So he was the great scientist in the last century, but we are the modern scientists. And we know fluctuations exist everywhere in this nature or in the universe. So I just proposed, compared with his totally homogeneous single temperature of universe, what could happen when there is a fluctuation of energy and matter? It's easy to imagine. In a big fusion machine, there is a smaller, more efficient fusion machine to have a higher temperature or higher densities. So neutron is diffused out. Elementary particle and nuclear reaction can go on in a different way to quickly create the radioactive nuclei, not only the stable nuclei, to reach the heavier nuclei, very 9. This is a kind of my prediction. I was very brave because I don't fear how great. I know he was great, but we are free to imagine getting to the truth. And since then, in 10 years or 20 years, world astronomers took interest in my predictions, and they try to verify which model is closer to the truth. Fluctuating model or George Gamow's homogeneous model. And at that time, I was still a very powerless young fellow when I was writing a PhD thesis. So I quickly wrote a request letter to my collaborators, Charles R. Koch, which is a professor of Harvard-Smithsonian Center, and also the George Fuller, who is a great professor of University of California, and asked them to push me to observe these elemental abundances by using a Hubble Space Telescope. And by using a Hubble Space Telescope, they could determine this. I was very happy to find this, but still, Japanese and Chinese collaborations by using ground-based telescope put the upper limit. So we don't know yet. My model or George Gamow model, which is better. So I'm now looking for the more data at the end, at the beginning of the universe of observations. James Webb Telescope would show us much earlier generation of stars to put the constraint. I may be killed, but if some data of James Webb Telescope will come around here below my prediction, I will make another model. Okay, now And this prediction of fluctuating in homogeneous model was 3 years before the discovery of CMB fluctuations by George Smoot. So he was awarded Nobel Prize because he discovered the fluctuations of cosmic background radiations. It was observations in the horizon scale, but we predicted not a horizon scale, much a smaller scale, and it is theoretical. However, the scientists are very fair to invite me next year after the Nobel Prize of George Smoot to invite many conferences about the cosmology. So our debate and friendship started in this way. Okay, now we have discussed a little bit about the beginning of a space-time universe and the first nuclear synthesis in the first 3 minutes. But after the universe was much more cooling down, CMB fluctuations were released into the space. And cooled universe can make the galaxy formation, and the dust is formed as the first stars, and the massive stars can explode, collapse and explode as a supernova, and leaving black hole or neutron star. If we are lucky, these black holes coming from one supernova and the second black hole from the second supernova can find a partner. Or neutron stars can find a partner to make a fireball again. So Big Bang fireball and the supernova fireball and neutron star merger fireball. These could be the site to create not only helium-4, helium-9, but also iron, gold, platinum, uranium, and thorium, which consists of our body. So all these fireballs are the possible site. But it has not yet been clearly identified which is a unique site of producing uranium and thorium. So this science is waiting for young fellows to come in to study. Okay, now let's move on. Again, my younger generation study. We have studied some of a Big Bang, but now, as I explained to you, there are many more objects to create atomic nuclei. And nearby fusion machine is the sun. So I was interested in what's going on inside the sun. If you want to go inside the sun, it is very dangerous. Don't do it. You are burned down in a couple of seconds. But by way of neutrinos emitting from solar fusion reactions, we could know what's going on inside the very, very high temperature, 10 to the 7 Kelvin center of the sun. And when I was writing my PhD, there was still a missing solar neutron problem. Here we show, as a function of ER, Davis Jr. and many other world nuclear physicists try to detect the neutrinos coming from the sun, which is called solar neutrinos. These blue are the measurement as a function of ER, and they are fluctuating because of solar cycles in heaven, so on. But the theoretical prediction is always twice or 3 times bigger. This was unsolved the biggest question almost 40 years ago or before. So here we show that William Farrar was awarded Nobel Prize about founding the nuclear astrophysics, connecting nuclear physics, particle physics, and astrophysics, and he got a Nobel Prize, and we met with him when I was writing a PhD thesis, and he suggested, oh, there are at least 3 possible solutions. The first one is you, nuclear particle scientists, are very ignorant. You don't know much about the reactions inside the sun. That is what he said. After getting Nobel Prize, Nobel laureate can say anything. You are idiot. And the second possibility is inside the sun, nobody knows the model of inside of the sun. And the third is some unknown nature of neutrinos can make this difference. There are at least three of these possibilities. And I was a student who loves neutrinos and also particle nuclear reactions, wanted to show this is correct or not. And I have done a couple of very precise nuclear reaction theories which predict, which emit neutrinos, and concluded within plus minus 5% precision, this overproduction is correct. Our best knowledge of nuclear reactions or particle reactions do not solve this difference by factor of 2 or 3. So I deleted this possibility. And the solar model, there is a very famous confident professor in the Princeton University, John Bacall. He has perfect confidence. My solar model inside the sun is correct within plus minus 1%. And after then, there are many more solar models constructed and verified his initial model was really correct. So the world astronomers rejected. Solar model immaturity was not the reason of this difference. So finally, some unknown nature could explain it. Yes, history is like that. In 1998, my colleagues, who is 2 years younger than I, in Koshiba School, discovered the neutrino mass and the oscillations, and he got a Nobel Prize. If my work was not done before, if John Bacall's solar model was not created, his Nobel Prize was delayed more. Science is like this. You should be very lucky. You should be very happy to collaborate. But many, many different aspects, science can verify which is really a unique solution or not. So we should work together and collaborate. It's quite important. If I talk too much, please give me 10 more minutes or 15 more minutes to say, but I will tell you just one story. 2015, I was watching the TV, the announcement from Nobel Committee. And in the evening, in the Eastern time, there was an announcement. This year's Nobel Prize is given to Kajita. Wow, great. Young fellow was awarded Nobel Prize. But quickly, my PC, emails noise, ringing a lot. Ping, 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 and I opened it. Then I received congratulation messages. Congratulations, Nobel Prize. Do you know why? My name is T. Kajino. His name is T. Kajita. Yeah. Anyway, all my good friends, our common friends, they know my name, his name, but I'm a little, 2 years older, so I have many more friends. When computer is very intelligent, when you put T. Kaji, so not Kajita, but Kajino was mis-emailed. Okay, so I now remember that night. I was very, very happy because my colleague, younger generation, was awarded Nobel Prize. Oh, if you tried your best, we can get the Nobel Prize someday. However, at that night, after receiving a long email, I wanted to have sake, drinks, and it was a little bit miserable night. Okay, anyway, this is one page of the story. So let us move on. Young generation, I would say you are very happy, very lucky, because here we show our famous teachers who discovered the theory of gravity and the theory of nuclear astrophysics. And Here we show the messengers of 4 fundamental interactions. Gravity, strong interaction, weak interaction, and electromagnetism. These 4 are fundamental interactions. And now, by the discovery of gravitational waves in 2015, messenger, gravitational wave, atomic nuclei, and neutrinos, and photons have all lined up. So they all are coming from any phenomena in the universe. So now, these phenomena and messengers are waiting for us to make a model. Let me move on to the story. When I was an undergraduate student, he was my mentor, and he gave me an instruction. Hey, Mr. Kajino and other guys, do the opposite of what others do. Don't follow the fashion. Keep your pockets full of dreams, okay? And you've got to hit one because your life is like a gamble. On drinking, he always encouraged me, please do, other than the opposite. The others do. It is very difficult. If there is a fashion, it's easy for you, intelligent person, to follow, to try your best to make a nature paper with laboratories. However, he suggested me, do opposite. And when I was a PhD student, Professor Arima was awarded a Bonner Prize, only a Nobel Prize he missed. He told me, don't follow the fashion, exactly the same, but open up your own new field yourself and help each other in the world. Firmly established science, you study first very, very seriously. Okay, Professor Koshiba told me, oh, it's a gamble, enjoy life. But Professor Arima told me, you study seriously. I was still fluctuating. Oh, which way is my way in life? But after I was written a PhD, he was awarded Nobel Prize in the same year, William Farrer at Caltech. And when I met with him, I gave a lecture. And he told me, oh, Taka, it's foreigners, easily to say. These 2 Japanese professors call me Mr. Kajino, looking down the student. Still, we are premature. But now, he's treating everyone equally. Taka, today's colloquium talk was very interesting. You have done a very, very good work on the solar neutrinos and the Big Bang. However, astrophysics and cosmology needs your imaginations more. Be brave to put even crazy ideas and let us discuss together. Okay, you understand my choice? After having these messages, gamble, enjoy life, and strictly study it. Now, his message changed my mind. Okay, we can enjoy the life of science based on a firm established science. So, I started based on astronomy, which is inductive, which means that finding the principle behind phenomena is the essence of astronomy, and physics. Physics derives a phenomena from fundamental principles. And this is from Arima Sensei's side. This is like a Koshiba Sensei's side. But now we want to combine to make a new frontier field, which is cosmo-nuclear physics. Of course, there was already established field of nuclear astrophysics. However, including elementary particles, particle cosmologies, we call it the cosmo-nuclear particle physics. So now I'm going on in this field in order to establish together with our world friend. Okay, now, here we show the nuclei. You may know this. There is a proton, neutron. Here is uranium, thorium, radium, and others, which were discovered by Marie Curie. and when, where, how they are produced in the evolving universe. That is what I'm now challenging in the cosmonuclear physics. And we have already discussed a little bit about the Big Bang. We have discussed the solar fusion reactions, but these are only a part. But we know more. Supernova or binary neutron star mergers, which are the second or third fireball in our universe to make probably heavy nuclei. So we are now challenging this. What is the present status? That is my mission to discuss with you. Okay, now, let me just briefly introduce the great discovery of gravitational wave. 10 years ago, the binary black hole mergers, probably binary black hole mergers were discovered because people detected gravitational waves coming from black hole mergers. Theory fit very well with observed gravitational waves. Gravitational wave was predicted 100 years ago by Albert Einstein, as you see, but now 100 years later, scientists can really find it was really a wave. Not yet, it is quantized. And the Nobel Prize was given to our teachers and friend teachers. So now I would like to insist, what can make this detection of gravitational waves? You may say, oh, laser interferometer, easy to change the deformation of space-time. But how small deformation they detected? Do you know? It is of the order of 10 to the 21 compared with, for example, the radius of Earth. This smaller ratio of the size, which is just the size of gold nucleus, the ratio of this radius of nucleus compared with the radius of Earth is 10 to the minus 21. This quality of precision measurement was realized 10 years ago. Now, please enjoy. How is a gravitational wave? Okay, now assume that somewhere binary black hole merged and emitting gravitational waves. And gravitational wave is now traveling through the sun, through the Earth. What kind of distortion of space-time in quadrupole moment was detected? Okay, I will show you demonstration. Now gravitational wave is passing. This deformation, it is at this level. It was really detected. Okay, Einstein and the particle nuclear theoretical scientists can easily predict, easily to say. But to detect this, it is not very easy. So this is a very good lesson that advanced high technology as well as a science of the laser interferometer made this successful detection of gravitational waves. So we discuss not only with scientists, but also the technologists as well. Okay, now I'm one of the Asian scientists. I'd like to say, now I'm going to discuss supernova or neutron star merger, how they are producing uranium and thorium, okay? What is needed? So the collaboration is needed. And here we show the two examples, collaboration over 2,000 years between ancient Chinese astronomers and modern astronomers. Almost 2,000 years ago, there was a document in China that supernova appeared, and the remnant would be RCW86. There was a document. And 10 years ago, the collaborating astronomers in Netherlands And Japan, United States, and many others found that how this supernova remnant is moving today. They very precisely measure the velocity of these expanding shock waves. And then, looking back in time, they identified, oh, it was exploded from one single point almost 2,000 years ago. That can match with a record of Chinese ancient astronomers. Okay, now let's come to our science. This is very famous supernova remnant, Crab Nebula, which was probably exploded 1054. There was a document in China or Japan. And having this description, one of my collaborators, who is a very famous supernova modeler, made a model. And we now apply our model based on these observations to the real nucleosynthesis of binary neutron star mergers. This can make a fireball, which was observed as a short duration gamma ray burst. There are many experts here. And also, the black hole forming supernova, single massive star also can make a long duration gamma ray burst. All these observations need modeling of the central engines. So we did it. Modeling all these merging processes or explosion or ordinary neutron star leaving supernova connected with a nucleosynthesis network code of particle and nuclear reactions, we can predict how the uranium, thorium around here is created to compare with observations. Okay, now move on. But there's one last task. Our universal age is 13.8 billion years. Very long. How to compare when, how, each of the objects can create uranium and thorium? It is a very difficult task. However, we tried to do that. Starting from star birth of star forming regions, once the star was born, depending on the mass, after some lifetime, it can eject some materials or explosion, and the mass is ejected into the interstellar gas. And then next cycle of the star was born. Like this. Okay, now we have made a model of each of the stellar evolution and explosions. Now we combine them into this cycle, which is called the cosmic and galactic evolution, to trace the 13.8 billion years history of evolution. Now I will show you. Oh, now already 1 hour has already passed. Oh, it is a relativistic effect. I think I talked only 10 minutes. Sorry. Give me 5 minutes. 5 minutes. Now having all these expertise of nuclear physics, particle physics, astrophysics, supernova physics, and cosmic evolution physics, we made a model. From the beginning of early galaxy as a function time in units of giga-year, we made a model. Here we show the heavy element abundances as a function of mass. This is platinum gold, which makes our wedding ceremony very happy. Here is iodine. When radioactivity is scattered, we put it into a baby to protect, against radiation. Okay, now this movie can show you very early galaxy, only a single massive star dominates. But as the time passes by, neutron star partner can find to merge and then catch up with the present day solar system abundances. So all these single massive stars and also the binary neutron star mergers can contribute. But now, my task is when in the history of universal evolution, they were contributed. In the past, no contribution from binary neutron star mergers. Only recently in the cosmic history, they can contribute. So we try to identify it. Okay, we will skip it. Again, we have a couple predictions here as a function of cosmic time from bottom to up. The different epoch has a different contribution from the different single massive stars or mergers. Okay, now we are waiting for verifications by using James Webb telescope or 30-meter telescope. We need observational astronomers' message to verify our cosmic history section. Okay, now, finally, let me show you the neutrinos. Neutrinos, Nobel Prize were produced by discoveries, but still we have many unsolved questions. Why neutrinos have mass? What is mass hierarchy? And why neutrinos are all left-handed and neutrino right-handed? These have not yet been solved. So how to solve it? In a couple of minutes, I will try to explain our try. This is related to the cosmology. In order to explain the acceleratingly expanding universe with the assist of cold dark matter and also the cosmological parameters, we need to know the mass of neutrinos because dark matter is probably a particle beyond the standard model, like a Suji dark matter. At the moment, only the finite mass of neutrino is the observables to show the need beyond the standard model. Okay, neutrino mass takes a key, and particle nuclear physicists try to constrain the total mass of neutrinos. Cosmology or neutrino-less double beta decay constrain the upper limit. But my idea is different. If you can study the neutrino flavor oscillations, we can constrain more strictly the total mass depending on the neutrino mass hierarchies. Okay, now, in order to do that, we have carried out the neutrino interactions inside the exploding supernova. Here we show inside exploding supernova, massive stars, there are hydrogen layer, helium, oxygen, magnesium, silicon, iron cores. And neutrino is streaming out in a couple of seconds. Our process occurred here. But in the outer layers, streaming neutrino interact with nuclei to produce this amount of nuclei. So in order to know the nature of neutrinos, we can use these nuclear abundances. Of course, we can't go inside the sun. Likewise, we cannot go inside the exploding supernova. Don't do that. But if we can detect the nucleus to be created by the neutrino interaction with matter, and then after ejection, meteorite scientists can find these elements, and then we can compare my theoretical prediction to know what's going on in neutrinos. This is the idea. Okay, time is running. Just one comment. If you like theory, you can study the Grashow-Weinberg-Salam standard theory of electroweak unifications. You may say, oh, it's easy to write down the neutrino interaction with matter. Hamiltonian, Lagrangian is simple, just one line. However, when you come to the exploding supernova, in a couple of seconds, 10 to the 44 number of neutrinos having 3 flavors and their antiparticles and in a different angles are streaming out. It is impossible to trace, even though you know the fundamental theory. By making some approximations, we did it by using a supercomputer. Okay. Now we make a movie. This is the radius just above the neutron star and out layer. When supernova exploded, And the neutrino is emitted. Shock wave is propagating here to produce these nuclei by neutrino interactions. Then secondary nuclear reaction destroy and produce this particle nuclear coupled explosion model of supernova can make the final answer. Okay, how to verify? Now we found inside the supernova, neutrino nature, one of nature inverted normal mass hierarchies can have a factor of 300 difference over prediction. We are very happy to find this difference. But the science starts from this theoretical prediction. How to verify how my prediction is correct or not. It should be tested by measurement or experiment. So I propose to compare with meteorite observations. Let me just give quickly. There are many different types of meteorite. However, we know that the X-type presolar grain is undoubtedly condensed and come from supernova ejecta. So we are now proposing, if the meteorite scientists can find big difference of our predictive elemental abundances, and this could constrain the neutrino natures. Okay, now time is up. I will just try to finish it. We started our discussion. Where are we from? Science answered partly. But if the science has a predictive power, we should predict our future. What the modern science predict? Our universe was probably started from symmetry breaking. CP violation, charge symmetry, parity symmetry were violated. Because of that, universe started. And the matter is more dominant than antimatter. So our universe consists of just a matter, not antimatter. This was due to the symmetry breaking at the beginning of a universe. This is our theory. What does this predict the future? If this is true, someday, even protons, which are inside our body, must decay, coming back to only neutrinos and the photons. So we are coming back to just a fireball. It's a very sad future. We would like to make a... That's right. Before that, human disappeared. Oh, yeah. Let us keep trying to survive. Okay, now, where are we from? This was first question. But now, almost 400 years ago, the Shakespeare said exactly the same question. And in King Lear, he wrote, oh, it is the stars above us govern the destiny of my 3 princesses. They were sacrificed. They were born under the destiny of different stars. But is it true? We discussed today, it is not the stars. It is a Big Bang, the Big Bang universe inside us govern our condition. Because, you know, almost 400 years ago, telescope, microscope were created, and now this is our tools. And what we found is the following. In the edge of the universe, we could find the fluctuations. But inside our body, inside the proton, there was a quantum fluctuations. And the scientists describe the symmetry breaking inside the microscopic world, and the early universe of microscopic universe are very similar. Okay, so we would say universe is something like a Ouroboros snake, as referred by Sheldon Glashow, Nobel Prize laureate. The macroscopic universe is governed by the law of microscopic principles, world. So you young scientists, there are a lot of things you should study. Relativity, classical mechanics, electromagnetism, down to quantum field theory and so on. One by one, please study. And then verify this scenario of a unification of space, time, and matter is really correct or not in our generations. Okay, now let me finish by sending you the message. Universe is a source of wisdom. Our science predicts that the universe is likely not eternal if you don't make any different models. We must accept the truth beyond us. If humans were not existing here, still universe was evolved. We accept it. But we should know what is the truth. And man has intelligence to think of the value of all creatures, not only human. And also, man acquires wisdom. Wisdom to create culture with scientific and technological powers. Okay, what's most important? Why do you study science? It is to think how to live. So my last message is, please think of every day after the lectures, how do you apply your knowledge to improve humans' culture and makes the future. So just let me lead. Let us share the wisdom beyond the nations. We are born to enrich our minds and tell the knowledge to our descendants forever until 10 to 33 years from now, hopefully, to overcome the difficulties. We know that everyone deserves worth living equally in peace. Okay, let us enjoy science more. Thank you very much.
Thank you. It was a fascinating talk, and we have time for only a couple of questions.